Are you excited? Because I'm excited, because today is Logarithmic Properties episode 1. Now, I will begin by not proving, but showing why a certain proposition is true. Now, I'm going to argue that f of minus 1 of x is going to equal x. And this will be because when you go to an output and then you come back to an input, you're back where you started. So I'm going to argue that a of log of a of x is equal to, now you're basically doing the same thing here. You're taking the inverse function and then you're going back to the input, or to the output in this case, is going to be equal to x. Now, I agree that this is not a proof, and this is actually a fundamental axiom that we will go through with in our proofs. Now, our first proof will be logarithm base a to the a will be equal to 1. Why? Well, raise a to the both sides. Now, a to the log of a is equal to, we'll give you this number specifically, so it's a. And a to the 1 is a because you're basically multiplying a one time, which is the same thing as not multiplying a, therefore it is a. And since our proposition led to a true statement, then our proposition is of course true. Therefore, logarithm a to the a is equal to 1. Now, this is our first statement. Our second statement will be logarithm of a of 1 is equal to 0. Why is that? Raise a to the both sides. These two will cancel. 1 will be equal to a to the 0. And a to the 0 is, well, it's kind of defined to be 1. Well, it's not. Well, it's a debate for another time. Maybe I will cover it another day. So it is going to be equal to 1, and we have 1 equals 1. And by the same logic, we have that logarithm base a to the 1 is in every case 0. Alright, now we have our second proof. Now, I actually invented a proof myself for this fact, for this lecture, because the conventional proof is so long, and it's counterintuitive as well. You have some p's, q's, a's, m, n, all of these kind of things. So let me show the proof that I invented. Now, what I'm going to prove is logarithm base a m times n is equal to logarithm a m plus log a n. So why does this hold? Now raise a to the both sides. This is m times n, and now this is equal to, now a, you can write this as a to the b plus c, and a to the b plus c is basically a to the b times a to the c, and the reasoning will not be explained here. Therefore, I can write this as a to the log of m, a to the m times a of logarithm a to the n, and these two will cancel out, giving you m times n is equal to, m times n. Therefore, you can say that logarithm base a m plus n will be equal to logarithm a m plus logarithm a n. And this is our third true statement. Now to our fourth statement. I will actually do it here, if that is visible. Yes, it is. Okay. Now, what the textbook argues is logarithm base a m over n is the same thing as logarithm base a m minus logarithm base a n. Let's do the same trick again. Raise a to the both sides. M to the n is equal to, I'm not going to go through it all over again like I did this time. Basically, the a's will cancel here, which will give m, and the minus will turn to a division, since, you're saying a to the b minus c is equal to a to the b over a to the c. Therefore, it's m over n. And this is true, therefore, our fourth true statement will be logarithm a m to the n is equal to logarithm a m minus logarithm a n. And we will use, not this one maybe, but I will be extensively using the third property in this course. Now, I will confess in something. I'm not proving any of the statements in the conventional manner. I know, I'm sorry. Now, here's how a mathematical proof works. You assume some axioms, and then you lead to the theorem that you're trying to prove is true. What I did here is assuming the theorem and then leading to some other facts such as 1 equals 1 or A equals A or M over N equals M over N. Some true statements. So I went back to some other true statements which I will declare as axioms. Like these axioms actually like coincided with my mathematical intuition. For example, I know from everyday fact that 1 equals 1, but this does not confirm a rigorous mathematical formulation, because you cannot assume the thing you're trying to prove when you're trying to prove it. Like this is, like I said, this is like me saying, well, if God exists, then these certain propositions are true. Well, sure it is, but you're not proving that God exists. In the same way, I'm not proving this statement is true. But in a rigorous mathematical formulation, you can do this rough work and go to the fact that A equals A, and then you can reverse all the steps to get the proposition that you're trying to prove, and that will be valid. That would be a valid proof. Now, why I haven't done that is because it's very counterintuitive way of thinking of mathematics, and it actually doesn't spare you any time to think, oh, I could have come up with that. Now, when you're seeing me writing these proofs, right, you're basically like thinking that, oh, I could have come up with that proof if I tried. But with this mathematical formulation, it's very hard to think of that because it's so rigorous and, counterintuitive to think about. So, again, that's why I'm not proving technically these statements, but showing why that they make sense. Anyways, thank you for watching and see you next time.